Hello again. Welcome to part 3 of section 2.6. Let's talk about radical expressions and solve a few equations involving radicals, and then we'll be done with this section. So, just as a reminder, I could say the square root of 9 equals 3 because 3 squared equals 9. So square root is the opposite of squaring. Remember, just like the absolute value bars, a radical is a grouping symbol. It's more obvious if I rewrite it as a power of 1/2. Remember, these mean exactly the same thing. Here you can actually see the parentheses. Here you just have to understand that this thing is a grouping symbol. So, just like with absolute value, if I'm trying to solve an equation involving a radical, first I want to get the grouping symbol by itself. So here I added 4 to each side. Now what I cannot do is something like subtract 10 from each side or subtract x from each side. I can't communicate between the inside and outside of a grouping symbol. The only way is to get the grouping symbol by itself and then interpret it by its meaning. So in this case, what that means, interpret it by its meaning, is this is a square root. Just like I could say, okay, if I square both sides here, I get 9 equals 3 squared. Algebra means maintain the balance of the equation. And so far we've done things like add, subtract, multiply, or divide each side by the same amount. But I could do really any operation to each side as long as it keeps the balance. So here I'm going to multiply each side by itself. I'm going to square both sides, because if these two things have the same numerical value, then their squares must have the same numerical value. So if this is true, then that's true. Now, I emphasized that, and I'll come back and talk about this a little more in a moment. So I squared both sides here. Root x plus 10 squared is just x plus 10. X plus 4 squared, we can FOIL. So first, x plus 4 times x plus 4, it's x squared. Inside is 4x, outside is 4x, and last is 16. So I'm getting x plus 10 is the same as x squared plus 8x plus 16. Now that's a quadratic equation. So what I want to do next is gather all the terms to one side so that the other side is 0, and I could use the zero product property. So I subtracted x from 8x to get 7x, and then I subtracted 10 from 16 to get 6. Now I showed 3 steps here, but really when you're working on your own time, the only reason I'm showing so many steps now is because this is the first time you've seen these problems, and I want to make sure no one gets lost. Generally, as you practice these for more and more time, you can start skipping a few steps. So skipping this step in the middle here would be perfectly fine. You can subtract the x and the 10 at the same time if you're comfortable with that. Anyhow, now we have a quadratic we can factor and use the zero product property. So I'm looking for two numbers that add up to 7 and multiply to 6. Of course, those numbers are 6 and 1. So either x plus 6 is equal to 0 or x plus 1 is equal to 0. One of those has to be true. So I'm just going to write this as x is -6. That would make the first one 0, or x equals -1. Now, the reason I emphasized this if-then in red is because normally when I maintain the balance, the operations are reversible. Let me talk about what that means. When I subtracted 10 from each side, that's a nice simple example. If this is true, then that's true. Like, if these are both equal, come on. If these are both equal, then these are both equal, because these are just 10 less than each of these respectively. And it works the other way too. To get from this to this, I could add 10 to each side. So if this line is true, then the previous line is true. And then I could add x to each side. If this line is true, then the previous line is true. So normally, every step I do is reversible. That means when I undo it, I don't lose any information. If x is -6 or x is -1, then the product of these two things must be 0. I can FOIL, add 10, add x, factor, and get back to here. So all of that is true. Here's the problem, though. If I tried to go from line 3 back to line 2, when you take the square root property says there's a plus or minus. Let me put it this way. Let me do an example. I could say 4 equals 4 comes from 2 squared equals 2 squared. And that's true. Since 2 equals 2, I can square both sides and get 4 equals 4. So since this is true, that's true. And since that's true, that means this is true. But on the other hand, if I started with a false statement like -2 equals -2, if I square both sides, I get 4 equals 4. So I got from a false statement to a true one. So what this means is when you square both sides, you're losing some information. You're losing the information about whether they were really the same or whether they just had the same magnitude, because either way you'll get a true statement after you square both sides. So what you could be doing is you could be introducing false solutions when you square both sides. Maybe root x plus 10 and x plus 4 are really the same number. Maybe they only had the same magnitude, and that's why I'm seeing that this is true. So what that means is I need to check these solutions and make sure that they really give me the same thing and not just the same magnitude. So I'm going to go all the way back to the very first line, plug these in and see what happens. If x is -6, then root -6 plus 10 minus 4 should be -6. And if x is -1, then root -1 plus 10 minus 4 should be -1. Over here, this says 3 minus 4 equals -1, and that's absolutely true. So -1 really does work. But over here, this is saying the square root of 4 minus 4 equals -6, and that's saying 2 minus 4 equals -6, and that is not true. So over here, root of -6 plus 10 is 2. -6 plus 4 is -2. So I have 2 equals -2. That's not true. But when I square both sides, I get 4 equals 4, and that's a true statement. So 6 satisfies this line, but it does not satisfy that line. That's called an extraneous solution. So squaring both sides is valid in the sense that if there are any real solutions, I will find them. But it introduces the problem of maybe this equation has more solutions than this one did. So you won't lose any solutions ever, but you could add an extraneous solution. So whenever you square both sides of an equation, it's imperative that you check your solutions at the end and make sure that they're real and not extraneous. Any questions here? Let me do another one then. Why did I ask for questions? This is a recording. Ingrained habit, my friends, ingrained habit. If you do have a question, ask me during office hours. My goodness. My goodness. Okay. That's probably not the last time I do that this semester. Let's solve this equation next. Nice thing is, the radical is already by itself. So the way I interpret it is I say, well, this thing is the square root of that thing. Well, this thing is the square root of that thing, rather. Let me square both sides and see what happens. So I get t minus 7 equals t squared minus 10t plus 25. And then I can add 7 and subtract t from each side. So when I subtract t, I get -11t. When I add 7, I get 32. So I'm looking for two numbers that add up to -11 and multiply to +32. Oh, whoops. Jeez, Nathan. That's impossible, of course, because I copied down the problem wrong. This minus should have been a plus. So I'm going to subtract t from each side, and then subtract 7 from each side, and this equation is solvable. This is t minus 2 times t minus 9. Much better. No, this is a plus 18, and that's how that works. Okay, sorry about that. Let's run through what we did one more time. We have the radical by itself, so we square both sides. There's a chance that that introduced extraneous solutions, so we're going to have to check later. And then I got this. This is a quadratic, so I want to gather all the terms to one side so I can use the zero product property. So I do that, and I find out either t equals 2, that would make this first factor 0, or t equals 9, that would make this second factor 0. So I know that those are solutions to the quadratic equation. I don't know if they're solutions to the radical equation, because this is more restrictive than this. If it satisfies this one, then it'll satisfy that one. But the reverse of that is not necessarily true. So I'm going to plug these back into the very first line. Root 2 plus 7 is 3, but 2 minus 5 is negative 3. So if I plug 2 into the very first line, I get 3 equals negative 3, and that's not true. But when I square both sides, I get 9 equals 9. So 2 satisfies line 2 by saying 9 equals 9, but it doesn't satisfy line 1. So that's an extraneous solution. How about 9? Root 9 plus 7 is root 16, that's 4. 9 minus 5 is 4. So not only does 9 satisfy the quadratic, it satisfies the original radical equation. So that's our correct solution. Sometimes you're going to get 2 working solutions. Sometimes you're going to get 2 extraneous solutions. It's just dumb luck that we got 1 and 1 each time. So you always have to check both and make sure they're not extraneous. So those are the kinds of problems that you'll see on the test. But I want to do a problem that's a little bit trickier just so you've seen it in case you see something like this in the homework. Oh, whoops. Want to make sure I copy this one correctly. When I copy the problems down wrong from my notes, then sometimes the solutions are not what I intend. So here I've got 2 radicals, and that's a problem. If I square both sides, then when I FOIL, first will be m minus 1, last will be 3m plus 1, but the outside and inside will be monsters made of 2 radicals multiplied together, and I don't want that at all. So before, we would isolate a radical and then square both sides to see what happens. And actually, that's what I'm going to do again. The way I'll solve this is I'll add one of the square roots to each side. So I'll have m minus 1 in root is equal to root 3m plus 1 minus 2. So I added this square root to both sides, and now watch what happens. This thing is by itself, so I'm going to square both sides. On the left side, I just get m minus 1, no square root. On the right side, I'm going to have to FOIL this and this. So first is going to be root 3m plus 1 squared. Outside is going to be negative 2 root 3m plus 1. Inside is going to be negative 2 root 3m plus 1. And last is going to be negative 2 times negative 2. So what I end up with is 3m plus 1 minus 4 root 3m plus 1 plus 4. So to summarize, what happened is I got one of the radicals by itself, and when I squared both sides, the isolated radical died. But the radical that had a friend stayed on in the middle terms of the FOIL. So if you're a radical, don't get isolated. Now what I'm going to do is I don't want to have any radicals left in this equation so that I can solve it. So what I'm going to do is isolate this other radical. M minus 1 equals, I'm just going to combine like terms in this step, 3m plus 5 minus 4 root 3m plus 1. And then what I can do is subtract 3m and subtract 5 from each side. Like so. So I subtracted the 3m to get negative 2m. I subtracted the 5 to get negative 6. And I don't like the minus signs, so I'm going to divide both sides by negative 2. Like so. Just easier to work with. I could divide by 2, but actually having a coefficient is lonely enough that I'm going to be able to destroy this radical. As long as it's the only term on its side, it doesn't matter that it has this 2 next to it. Look, when I square both sides, I get m plus 3 squared equals 2 root 3m plus 1 squared. But that's really just the same as 2 squared and root 3m plus 1 squared. So having it with a coefficient is enough. I don't have to divide by the 2 if I don't want to, because this square is going to get rid of this radical anyway. So m plus 3 squared. Let's FOIL. M plus 3 times m plus 3. You can check yourself. It's m squared, and then 3m and 3m makes 6m, and then 3 times 3 makes 9. On the right here, we have 4 times 3m plus 1. Because 4 is 2 squared, and 3m plus 1 is this radical squared. So we had to isolate a radical, square both sides to kill it, isolate the other radical, square both sides to kill it. Well, now this is just a quadratic, so I can simplify. I distributed the 4. Now I'm going to gather all the terms to the left. That's going to leave me with a 0 on the right. So I'll subtract 12m from each side, leaving me with 6m. I'll subtract 4 from each side, leaving me with a 5 here. And now I can factor and use the zero product property. Two numbers add up to negative 6 and multiply to 5. That makes negative 1 and negative 5. If m minus 1 is 0, sorry, there it goes. If m minus 1 is 0, then m equals 1. If m minus 5 is 0, then m equals 5. One of those has to be 0 for the whole thing to work out to 0. So m is 1 or m is 5. But remember, we squared both sides, and that has a chance of introducing extraneous solutions, like I explained before. So I have to go all the way back to the original problem, which I'll copy down here. It was m minus 1's radical minus radical 3m plus 1 equals negative 2. So let's check and make sure that each of these works. If I plug in 1, I get root 1 minus 1 minus root 3 1s plus 1. So this is root 0 minus root 4, which is 0 minus 2, and that really is negative 2. So that one checks out. Let's try m equals 5. That would say root 5 minus 1 minus root 3 5s plus 1 equals negative 2. So that's root 4 minus root 16, which is 2 minus 4, which really is negative 2. So this time, we got lucky, and neither of these solutions was extraneous. They both work out, so we're going to report both of them. Either one of those values of m will make the original equation true, rather. And that's how you solve equations containing radicals. Join me next time for inequalities.